From this example, a spring is set 100 millimeter by a 20 kilogram block. It means that this is the I define the equilibrium position. Okay, so equilibrium position, this position is defined. Okay, the free body diagram is maybe like this. Okay, it means that this length, this position is ys. The deformed length from the unstretched position is equal to 100 millimeter. Okay, so the equilibrium position for the free body diagram of this is have the spring force and has the gravity, that is mg. Okay, this is the free body diagram at equilibrium. At equilibrium position, so over here. Okay, so then at the first step, we, for this case, we don't know the spring constant. If we don't know the spring constant, we have to determine the spring constant first. Okay, so for this case, we don't know. We have to determine the spring constant from the equilibrium position. Okay, same as the building design. Okay, we may have to determine the spring constant of the building from the equilibrium position also. Okay, so then if we consider equilibrium position, from equilibrium position, we found that summation Fy becomes 0, right? Okay. Okay. Right now, we may set up downward. Okay, downward as the positive. Okay. Downward as a positive. So then we may set up the positive sign convention, follow the kinematic. Okay, so then downward is positive, it's become mg minus fs. It's become 0, right? Because it is equilibrium. It's in equilibrium. Okay, so according to this, we can find that fs is equal to mg. Okay, but fs from the spring force is equal to kys equal to mg, right? So according to this, it means that k is equal to mg divided by ys. Okay, so right now what k should be? Okay, so according to this example, k should be what? K should be 20, right? Okay, 9.81 and divided by 0.1. Okay, let's become 1962 Newton per meter. All right. Then we already know the stiffness K already, right? Okay. From the equation of motion, is the second step. Okay. Second step, we consider the motion. That is, we consider the third position. The third position, that is we have the displacement from the equilibrium position equal to y. Okay, so then we consider the equation of motion. Equation of motion at displaced state. Okay, we found that from equation of motion at displaced state, we found that equation of motion is become my double dot, right, plus ky equal to 0 for this case. We can rearrange this equation to be y double dot plus k over m y equal to 0, and we define this term as the natural frequency. Okay, natural frequency. So at this step, we will determine omega, that is the natural frequency. Okay, this term identify natural frequency that's represented by omega. Okay, so now omega has become what? This term is omega squared, right? Okay, so then omega, that is natural frequency, is what? Is square root of this term, k over m. Natural frequency is omega, okay, but k over m is the omega square, okay. So for this case, omega is become what? It's become square root of 1962 divided by 20, right? And it's become what? It's become 9.90454, right? Radian per second. It's for this case. Okay. Then we move to the third step. Third step, that's we consider the general solution of this equation. Okay. General solution of this equation, of the equation of motion. The general solution for this case is a free vibration. General solution is defined by y equal to a sine omega t plus b cosine omega t. Okay, we can find that we have two constants, a and b. Constant a and b is determined from the initial condition. Okay, initial condition for this case is state from when time equal to 0. Initial condition. When time equal to 0, y equal to what? 0.15 meter downward. Okay, so then it is a positive. And when time equal to 0, velocity it's become what? It's become 1.5 meter per second downward also. Okay, so this is positive. Okay. So from initial condition, this is the initial condition. Because we solve the differential equation, this is the second order differential equation. So then it is second order, you have to integrate this equation second time. After we integrate, second time is mean that we obtain two constants. Okay, so then if we have two constants, we require two conditions. The condition that we require, for this case, this is the initial value problem. we call it is a initial condition because the condition occur at the same time. At the time equal to 0 at the same time, we call this type of problem as the initial condition. Okay. So from the initial condition, we have two conditions, right? When time equal to 0, y equal to 0.15. When time equal to 0, velocity equal to 1.5. Okay. We consider the first condition. Okay. From the first condition, that is when time equal to 0, y equal to 0.15. Okay. So then what does it mean? It means that if we apply this equation, okay, substitute time equal to 0. So then y is equal to 0.15. Okay, and equal to a sine omega t is 0, right? Plus b cosine omega t is 0, right? So then cosine omega times 0 is become cosine 0. This is equal to 1, right? But sine omega times 0 is become sine 0. Sine 0 is become 0, right? Okay. So then what does it mean? It means that from this condition, from the first condition, we conclude that b equal to 0.15 meter. Okay, b equal to 0.15 meter. Okay. So then we consider the second condition. The second condition is when time equal to 0, v equal to 1.5 meter per second. Okay, v is what? V is the first derivative is y dot. That is dy by dt. Okay, dy by dt is become what? From this equation, we take the derivative over here. It's become a omega cosine omega t minus b omega sine omega t. Are you right? Okay. According to this, it means that when we substitute time equal to 0, v equal to 0.15. Okay, so then it's become 0.15. Oh, sorry, 1.5. Sorry, v equal to 1.5. 1.5 equal to a that we don't know right now. Omega we already know. Okay, cosine omega t. Right now we substitute t equal to 0, so then this is 0, right? Okay, it's cosine 0. Actually, cosine 0 is 1. Okay, and minus b that we know it already is equal to 0.15. Omega, that's actually we know it already, and sine omega t is equal to 0, so then sine 0. So that means it means that this term is 0, right? Okay, this term is 0 because sine 0. I have to this instead. Okay, so that means it means that at this point we can conclude that a is become what? A is become 1.5 divided by 9.90454. So then a is to become 0.15145. Are you right? Okay. Now we have a and b already. So then we almost done. Okay. At the final step, This is what? This is to complete the equation. Complete the equation. So then y is equal to what? For this case, y is equal to a sine omega t, that is 0.15145. Okay, sine omega, substitute omega equal to 9.90454 t. Okay, plus what? Plus b, that is 0.15. Okay, cosine 9.90454 t. That's all for this. This is the first answer. Okay, and then the phase angle. The phase angle is what? The phase angle is the arctangent B over A that is become of 0.15 divided by 0.15145, and it's become, okay, if you don't if you don't change the setup in your calculator, it's maybe in degree. It's maybe equal to 44.72 degree. But you have to answer the angle phi in radian. Okay. So angle phi in radian, you have to convert the degree to radian first. Okay. Change it to be radian is equal to what? Okay, we know that. We know that 180 degree is pi radian, right? Okay. So then what does it mean? It means that 44.72 degree should be what? It should be 44.72 times pi divided by 180, right? So then angle phi is become 0.1, okay, 44.72 times pi divided by 180, 0.78, okay, 0.5, okay, radian. Okay, according to this, we can conclude another solution, that is the alternative solution of y. This is the alternative one. Of y. Y is become what? We determine the amplitude. Okay. Amplitude C. C is the amplitude. C is equal to what? C is equal to square root of A square plus B square. That is become 0.21316 meter. Okay. So then the solution, we can rearrange this equation to be this instead, that is 0.21316, okay, sine, okay, omega t 9.90454 t, okay, plus phi, that is 0.7805, okay. Have to note that the angle phi in this term has to be radian, okay. You cannot use this, okay, because it is in degree. But in the equation that describes the motion of the system, the phase angle should be in radian, okay. Okay, be careful to apply it, okay. So then this is the alternative solution, but the question is stopped at this point already, okay. Actually, you answer only this and only this. That is okay. That it should be enough. Are you all right? For this is all for this example.